Thank you very much. I'm Jordi Torrents. I'm a PhD student in sociology at University of Barcelona and also a NetworkX developer. So in my research, I'm focused on collaboration networks, mostly co-authorships between scientists and also collaborations between developers when building open source software packages. During this research, one of the things that I wanted to look at is at the cohesion of the groups of people, being scientists or developers, while working in this kind of collaborations. The thing is that sociological theory about group cohesion is not a very, there are very different approaches to cohesion, and what they have in common is that the use of the concept of cohesion is not well defined. If you look closely at these kinds of uses in empirical analysis in sociology, most of the time people doesn't use a definition of cohesion. Is usually an implicit definition which only fits the empirical analysis, which is the focus in that concrete paper or research. This, of course, is a very big problem, especially if you want to compare cohesion in networks, collaboration networks, which are different. For instance, co-authorships in science or collaboration in open source. This problem has been known a long time, and since the early 90s and late 90s, several sociologists started to look at this problem and try to find a definition of cohesion that can be applied to several settings and to make explicitly a definition of what cohesion means. One of these early efforts is a nice book from Dorerian and Ferraro in 1998, in which they divide the concept of cohesion in two components. The first one, the ideational component, is based on members' identifications with the collectivity. And this has been historically the main focus of the sociological analysis. But they point out that there is another important component, which is the relational component, which is based in the patterns of relations between the members of that community. From a social network analysis point of view, the relational component is a lot more, is a better approach to try to define cohesion in social groups with some kind of quantitative measures. Actually, if you look at the literature of social network analysis, we see a lot of measures that have been used to quantify cohesion in social groups. There are the classical measures like cliques, clans, clubs, etc. And more recently, the community detection analysis algorithms in networks have also been used to try to analyze this kind of the cohesion of social groups. The thing is that when you look at the sociological literature of group cohesion, neither of these approaches, nor the classical and also the new ones, allows us to analyze, especially these collaborations networks in which I'm interested, to analyze the key features of the cohesion. And these key features of the cohesion are mainly three. The first one is robustness. So a qualification of a group should not depend on the actions of any individual. If you look at this star graph, one of the focus of the sociological literature on group cohesion was focused on groups with a charismatic leader. And if you look at this representation, the charismatic leader is the only actor that holds the group together. So we cannot consider, at least for my research in collaboration networks, this kind of cohesion doesn't allow us to model the kind of cohesion that you might expect to find in this kind of collaboration networks. If you look at the complete graph that is below the star graph, is more the kind of network in which you would expect that is a very cohesive group, because each of the actors of the group has multiple relations to the other members of the group, and if you remove any of the actors, the group continues to hold together. The second feature that a cohesion measure should have is overlap, because if you look at the top figure on the overlap, there is a very influential book by Ronald Barthes, which is Where Do Good Ideas Come From? And the point of this book, or the main point of this book, is that there are actors that connect different groups, and the flow of information of different groups have to go through that actor. The point of that book is that good ideas come from the actors that make this brokerage between groups. But more recent sociological theory has found that groups that overlap, like in the case of the figure below, if an actor is actually part of the two groups which he is linking, then it's not only the flow of information, but the actions of the actors involved. And therefore, a measure of cohesion should allow us to distinguish these two factors, and should allow for different groups to share some of the actors. And finally, a cohesion measure should be hierarchical, in the sense that when you go to empirical settings like co-authorships in scientific networks, or collaboration between developers in open source communities and projects, you see a core development, a core set of factors that does most of the work, but that is surrounded by other less cohesive parts of the network that play the role of periphery. So being able to analyze and to detect quantitatively these kind of features, there are not many sociological theories that allow this. One exception to this is the structural cohesion model, which is, was formulated in the early 2000s by White and Harari and Moody and White, in which they based the definition of cohesion in the graph theoretic measure of node connectivity or vertex connectivity. And this is a precise definition of what do we mean by group cohesion, and it has an equivalence relation, because you can, if you know graph theory, there is the Menger theorem, which says that these two definitions are mathematically equivalent. A group structural cohesion is equal to the minimum number of actors who, if removed of the group, would disconnect it. And also, a group's structural cohesion is equal to the minimum number of node-independent paths that link each actor in the group. This theoretical conception of group cohesion is very useful for the kind of analysis that we would like to do in this kind of collaboration networks. And it has a very clear and quantitative way to assess and to compare different networks from different fields, and has these key measures: the node or vertex connectivity, and also the K components, which is a maximal subgraph that has node connectivity K. Note that this definition of K components is hierarchical. So the red nodes in the middle, there are 9 nodes there, and you have to remove 4 if you want to disconnect the group. But this group of 9 actors, which is embedded in the core of the network, is also part of a less cohesive group, in this case the blue nodes, in which you only have to remove 3 of these actors to remove the group. So this, the fact that having a clear quantitative way of defining cohesion in social networks allows for empirical analysis, and we have several examples here in which applying this theoretical conception of group cohesion allows to analyze interesting empirical settings which are far from collaboration networks, from science and from software development, but are very interesting. The thing is that there are some problems with this model. The first one is the computational complexity of these kinds of computations. Most of the empirical analyses that have been published are only several hundreds of nodes and edges. And when I'm looking at the co-authorship in scientific co-authorships and software development, the order of the networks are of the order of the thousands or tens of thousands. And besides that, there is also no implementation in the popular network software packages that does this kind of analysis. So what I did is implement an exact algorithm for computing the K components on top of NetworkX, and the exact algorithm is based on a very neat algorithm of Kanevsky, which finds all the minimum size node cuts in a graph. If you see this two-dimensional grid at the top, the red nodes are the minimum size cut sets, so which have cardinality 2, and if you remove these red nodes, you disconnect the group. The thing is, the algorithm for computing K components is based on keep applying this algorithm, this Kanevsky algorithm, until you have a trivial graph, so you cannot cut more. The thing is that when I try to apply this algorithm to the kind of networks in which I'm interested, of the order of a few tens of thousands of nodes and actors, then I was not able to compute it. For this, we have been working in a set of heuristics which allows to analyze networks up to the tens of thousands of nodes. These heuristics are based on an approximation of local node connectivity, which I also implemented on top of NetworkX, which gives you a lower bound on the node connectivity. And this is usually, it's usually better to have a lower bound, even if you don't have an exact number, but at least you can analyze the kind of networks in which I'm interested. So I will skip a bit the logic of the heuristics, but if you are interested, there will be a paper in the proceedings in which I'm describing all the details, both of the exact implementation of the algorithm and the heuristics. And let me say also that this will be released with NetworkX 1.10, which is actually now in PyPy, so you can install if you want to play with this. And because I'm very late, I will only show you a bit of the kind of analysis and the kind of networks in which I'm interested and over which we applied this kind of analysis. So for instance, here are two kinds of networks, collaboration in maintaining packages in Debian and scientific authorship networks from high-energy physics theory and nuclear theory. And if you look at the table, the main point is that the number of nodes and edges is of the order of tens of thousands, and you can compute that in a laptop like this one in more or less 1 hour. And very quickly, let me show you the kind of graphical representation that this kind of structural cohesion analysis looks like in social networks. It's usually defined each K component, remember, which is a maximal subgraph with node connectivity K. You draw one node for each one of the K components and an arrow which links a K component that is nested inside another K component. This is the case of Debian, and this is the case of nuclear theory. And very quickly, to finish, one thing that we also been working is in a different graphical representation of this kind of analysis using the very nice three-dimensional scatter plots from matplotlib, in which you can draw a dot for each node in the network, and then the z-axis, the vertical one, is the average connectivity of each one of the K components. And the main point here is that it's easy to distinguish an organization, like the case of Debian, in which you have G and K components in which most of the developers are in, and which is very different of a scientific field in which you have many K components because there are many groups of scientists that work in the same field. And that's it. If I have time, I will take some questions.
Thank you, Jordi. Do we have any questions?
On your graph there, what are the X and Y coordinates?
Okay, the X and Y coordinates are the result of the Kamada-Kawai layout algorithm. So a force-based layout algorithm, the one that you use normally to draw a two-dimensional drawing of a network. And then the important part is the z-axis, in which you can put, in this case, is the average connectivity, but you could use this with another measure if you are interested in centrality measures, for instance, betweenness or whatever.
And I was wondering, like you said, you were studying open source communities like us, I guess.
Yep.
How do you collect the data on the networks for that? Did you see Sebastian Benthal's tool that he's developing to scrape mailing lists and things? Yeah,
I found it very interesting, but I'm looking at the Git repositories directly and how different developers work in the same file. I think that the approach of the Big Bang is to focus on mailing list, which from my perspective is not as interesting as the actual contributions of code on different parts of the open source project, because I think that for making an analogy with co-authorship in scientific networks, it's better to look at the collaborations in concrete parts of the open source project.
Great. Thank you very much.
Thank you.